So first of all, can everyone hear me okay? Okay. So thanks very much for the invitation to come and speak with you today. It's great. This area is fantastic because there are so many Earth and planetary scientists around, and it's been really great to kind of go around and meet all the different people. So today I'm going to be talking to you about the moon, and specifically trying to understand a big issue with the magnetic fields that we see in the crustal rocks on the moon. Those magnetic fields come from a long time ago. So we're going to be talking about the ancient lunar dynamo, the source of that magnetism. And specifically, there are these two what I'm calling conundrums. First of all, there's an issue with the intensity of the magnetic field you would have need to have to explain the crustal magnetism and the length of time that the dynamo was active. A lot of the work that you're going to see was done by my former graduate student, Bob Tian, who's moved on to more lucrative startup data science type work. And my other collaborators are Sonia Tiku and Ben Weiss on this project. So here's a map of the lunar crustal magnetic field. This is showing you, this is from data from a combination of data, but there's data we have for the magnetic field from Lunar Prospector and the Kaguya spacecrafts, as well as we have rocks magnetism from the Apollo missions. But here's the near side of the moon, and here's the far side of the moon. And what you're seeing here is a map of the total magnetic field strength. So reds and greens mean strong magnetic fields, and blues and purples mean weak magnetic fields. What you can see is that there are regions of the moon that are very strongly magnetized, but there are regions, splotches all over that do have magnetism. So this is the lunar crustal magnetic field. We also have information about the moon's magnetic field from samples. So the Apollo astronauts brought back about 370 kilograms of lunar rock samples. Here are the listings of the different mission landing sites. This is Bob. He's holding, he went to some lab and got to play with the meteorites. And so here, well, not meteorites, sorry, the samples. So here are some of the lunar samples. And so from these rocks, we can actually do modern paleomagnetic analyses of them and try and learn about what the magnetic field on the moon was like in the past when those rocks cooled. And if you do that, you get a graph like this. So on this graph, this is time before present. So today is somewhere over here. This is 1 billion years ago. Here's about 4.4 billion years ago. And on the y-axis, what I'm plotting here is the intensity of the surface magnetic field that you would have needed in order to magnetize those rock samples, okay? And from what you see here, you've got some rock samples. The oldest one we have a magnetic measurement from is about 4.25 billion years old. And then there's some samples here, and then you can see we've got a few samples here. And there's one sample here that has a really large error bar in age as well, okay? And these are all from recent reanalyses using these modern paleomag methods of the rocks. Now, if you look at a map like this, I want to point out two features. Okay, first of all, there seems to be this epoch early in lunar history where the magnetic field strength at the surface of the moon was quite strong, around 10 to 100 microteslas. Okay? Then, afterwards, there was a time later, from about 3.5 onwards, where the field was much weaker and possibly for these points even zero. So these points are actually just upper bounds on the possible magnetic intensity of the field. Having a zero intensity field would have been okay for these ones. All right? So there seems to be these two epochs in the lunar magnetic history. Now, the only way to explain a long-lived magnetic field on the moon during this time is through a dynamo process. And the basic idea here is that you have complex motions in electrically conducting fluid in the core of the moon. If you have a presence of magnetic field, then those motions can interact with those magnetic fields and regenerate them faster than they decay through ohmic dissipation. So that's what you call a self-sustaining dynamo. And this is really the only way to explain the long-lived fields. It is possible that impact-induced plasma fields could explain some of the magnetism that we see on the surface, but it couldn't explain the Apollo sample magnetism, which required a long-lived stable field in order to explain how the whole time that the rocks cooled through their blocking temperatures. Okay? All right, so if we're going to invoke a core dynamo in order to explain the lunar magnetic record, then I would argue that you need to explain the following three facts with your core dynamo mechanism. First of all, you need to explain this high field intensity epoch here. Okay? Then you need to explain a low field intensity epoch later, and I would argue you also need to explain that there's no dynamo today on the moon. Okay? So those are the three basic facts of the lunar magnetic field that your dynamo mechanism better be able to explain. So when we're talking about dynamo mechanisms, what we're really talking about is what is the source of energy for the fluid motions in the core in order to generate the dynamo. Okay? And as a dynamo theorist, the first one you go to as a possibility is thermal driving. And the idea here is if this is to represent the core of the moon, so this is the center of moon and this is the core mantle boundary of the moon, then if you have a temperature gradient across here, then you can drive thermal convection in the core, and these could generate a dynamo. Okay? Now, if you do that for the moon, then you can come up with estimates of how long the dynamo could have lasted from the thermal convection, because as the moon cools, eventually you will get subcritical for the thermal convection. And simple estimates of this, a standard model of this, tell you that thermal convection ends somewhere between about 4 and 3.8 billion years ago. Okay? But you can modify this standard model. You can do things like make a water-enriched mantle or have the core mantle boundary of the moon initially be thermally blanketed by radiogenic heat sources. And so you can delay the turning off of convection with this method. And if you do that, you can make thermal convection last much longer, so up to about 2.6 to 2.5 billion years ago. So in this case, you might be able to explain the longevity or all these points, samples that we have. However, if you estimate how strong the paleo field would have been from this driving mechanism, and you can do this from scaling laws that are developed from dynamo theory and dynamo simulations, then you end up finding that the intensity of the surface field you would expect from a thermally driven dynamo is about this range here. So it's about less than 1 microtesla. So what you can see from this is maybe we can explain these points, but it's very hard to explain the high field epoch with a thermally driven dynamo. Okay. So if that's not going to work for us, then the next thing we typically try is compositional driving. So the idea here is that if you have a solid inner core forming as the moon is cooling, then you're going to preferentially release light elements at the inner core boundary, and those can drive convection in the outer core as well. Okay? And if you do this with simple thermal evolution models, you can find that the compositional convection can last for this entire time and drive a dynamo through this entire time. So that's good. In fact, some of the models continue lasting until today, which is bad. Okay? So you need to tweak your model a little bit so that it actually stops working eventually. Okay? But again, if you then estimate how strong the magnetic field would have been from this mechanism, you end up getting estimates down here. So these are from 2 different studies with slightly different parameter values, but basically you can't get much higher than about 1 microtesla field strength at the lunar surface. Okay? So again, it's a challenge to explain the high field epoch points, but it could possibly explain the low field epoch points. Okay? So if those 2 mechanisms aren't going to work, as dynamo people, we're kind of forced into this regime that we, for a long time, shunned, okay? But we really have no other possibility here. And that's that you could actually drive a dynamo through mechanical driving. So what that means, if again this is the core of the moon, that at the core mantle boundary, if you have any sort of differential motion there, then you can actually put power into the core motions at this boundary, which could then cause churning motions in the core. Okay? These differential motions, the source of them, there have been a variety of them that have been proposed in the past. For example, it could be due to the moon's precession, it could be due to tides, libration, or impacts. Okay? Now, the reason that this was shunned for a while is there was some early work done on this. People suggested that this could actually drive the Earth's dynamo for a while. But the early work found that the types of fluid motions that you get from these mechanisms are typically too simple. They cannot generate dynamos. You actually have to have fairly complex motions in order to get a dynamo that's self-sustaining. And these motions that were initially found were too simple. Okay? However, recent experiments and simulations have found that there are instabilities that could develop along these very simple flows that do have the right sort of complexity that you need in order to generate a dynamo. So it's become more in vogue recently to start considering this mechanism because we realize that you could actually get fairly complex fluid motions from these very simple driving forces. Okay? However, this field is still sort of in its infancy. Okay? There are experiments trying to work out what sorts of flows you get, what sorts of instabilities you get at different parameter values. There are simulations trying to find existence proofs in the sense that here's the type of flow we get. Could that flow generate a dynamo? Okay, so this is really sort of at the stage of a starting field, a growing field, which is good, but it's not clear that the motions that you get from these types of mechanisms could actually be very efficient at generating dynamos. So that's sort of where we stand there. Now, just to give you some ideas of some of these mechanisms, one of them, which was proposed by Labars and colleagues, is that you could drive dynamos at intermittent times in the lunar past through impact unlocking. So the basic idea here is if you've got the moon, and if a large impactor comes by and hits the moon, it will temporarily unlock the mantle from the core, and that will cause that differential motion at that boundary. And so they did studies to see whether or not you could actually reach critical values for magnetic field generation in these types of models. And what they found, for example, this is just sort of a parameter space study from their work, but what they found is they could get field intensities up to about 3 microteslas, okay, but only in that short period of time when you had very large impacts, okay? So again, this is problematic because it doesn't seem to be able to explain the high field epoch. It's problematic because in temporal space, it can't explain the entire record, but it might be responsible for some of the lunar magnetic anomalies we see, especially those associated with craters, which would have formed at that time, melted, and had their melt sheets remagnetized in the field at the time. But this mechanism is not going to explain the high field epoch. At least it's not obvious how it can do that. The mechanism I'm going to focus on, which we looked at, is driving the dynamo mechanically through precession. Okay? So the basic idea here is that the mantle of the moon, its orbit is precessing. Okay? And there was some work done on this, looking at how much power is available to the dynamo through this precessional mechanism. This is a study by Dwyer and colleagues. And what they found was that as the moon moved away from the Earth, and I'll show you this in more detail in a minute, but as the moon moved away from the Earth, the power available through precession would have declined over time. So, and there seems to be enough power to explain this high field epoch, and then also the decline to the low field epoch. Now, their work essentially involved looking at how much power was available from this mechanism, and then plugging those into scaling laws that were developed from convection-driven dynamos, and seeing whether or not they could get the right field intensities. Okay? So they didn't try to solve for what the fluid motions would have been in the core from this mechanical driving, from this precessionally driven flows. So it's not clear that the scaling laws that have been produced from numerical simulations that are convection-driven will necessarily also work for mechanically driven dynamos. Okay? So there's still this open question as to whether or not you could actually fit this using that scaling law. But it seems to have potential, right? Because it seems to be able to give you the high points and then the reason why you no longer have the high field. So our goal was to try and produce precession dynamo simulations that were relevant to the moon and also be able to determine the field strengths and longevity. So we wanted to try and do this the hard way, or the right way. I will tell you right off the bat that the initial conclusion to this was we failed. Okay? It's important that we talk about all these times that we fail in our research, right? We have a great idea and it doesn't work, okay? So we failed, but something good came out of it, and there was success after, so that's good. So you can get success out of failure. And it turns out in the end that it makes sense that we failed, okay? So that's good. All right, so I'm going to talk you through this. This is just a schematic of the moon's interior. We have information about the lunar interior from a variety of sources, including seismology, magnetics, laser ranging, and gravity. And they all tell us, so for example, the moment of inertia of the moon is very close to a homogeneous value of 0.4, which means that it has a very small core. We know that the moon can't have a large core. From seismics and magnetics and laser ranging, we know that there's a fluid region in the core, okay? And seismics recently, in a paper by Weber and colleagues in 2011, suggested that there's also possibly a solid inner core, okay? So we know we have the right ingredients for a dynamo in the sense that there is a fluid outer core, and there might even be a solid inner core today. Who knows in the past, okay? So that's the scenario we're working with. Also notice that the lunar core is small. The radius of the core mantle boundary here is about 330 kilometers in their model from the seismic data. All right, so in order to understand the processional driving, we need to talk a little bit about the lunar orbit. Here is a sketch of what the moon is doing today. So this represents the moon. This is the orbital plane of the moon. So this is the orbit normal to that plane. So the Earth is somewhere over there, okay? But the Earth-Moon system orbits the sun about the ecliptic. So this is the ecliptic plane, so the sun would be somewhere over there, okay? And today, the orbit normal of the moon precesses about the ecliptic normal of the Sun-Earth system, and the angle between those is about 5 degrees, and the precession period is about 18.6 years. So that's the scenario today. And the reason for this orbit precession is that there are gravitational torques that act on the moon, both from the sun, the fact that this is inclined relative to this, and also from the equatorial bulge of the Earth. Okay? Now, the moon also is in a very interesting and also standard type of configuration known as a Cassini state. And the basic idea here is if you have a body that can tidally dissipate, you're going to end up in a state where the orbit normal, the ecliptic normal, and the spin axis of the moon all become coplanar. Okay? So these three vectors always have to form a single plane. If you were to view this scenario from above, that's what I've tried to draw here, where the blue represents the ecliptic normal, the white is the orbit normal, and the yellow is the spin axis. You can basically always draw lines at any point in time between these three. Okay? What this means is that the spin axis and the orbit normal co-precess about the ecliptic normal as a function of time. Okay? And this is only possible at certain spin angles. So you can actually figure out what the spin axis of the moon has to be in order for the Cassini state to be valid. Okay? Today, that spin axis about the orbit normal is about 6.5 degrees. All right, but the moon has been moving away from the Earth since its formation. And as that happened, the gravitational torques changed because of distance changes. Okay? So what you can do is you can solve for what the spin angle, so this is the obliquity of the moon, would have been as you go back in time for the Earth-Moon system. So on this axis, what I have is the semi-major axis of the moon in units of Earth radii. So this is distance between the Earth-Moon system over time. Here we are today. Okay? And the lines on here are the equilibrium states, the stable solutions of the Cassini state scenario. Okay? So today there's only one stable solution, and we live here at about 5.5 degrees. Okay? Or well, 6.5 from the orbit normal. Okay? But as you go back in time, and in fact when the moon formed, say somewhere over here-ish, okay, there were actually more available equilibrium states. And in fact, the state that the moon was most likely to form in, the one that had the largest basin of attraction at that time, was state 1. So initially, the spin axis obliquity was likely close to 0 in this state. Okay? But as the moon moved out, it would have had to remain on this curved line. Okay? And you can see that something is going to happen around this point here. Suddenly, there's nowhere for it to move on anymore. It can't go back. It's not going back to the Earth, right? So instead, it has to jump to the only other stable state available at that time. And so it transitioned from Cassini state 1 to Cassini state 2 at or around 30 Earth-Moon separations. Okay? So if you were to plot the path of the lunar spin angle as a function of time, you would see it close to 0, then jumps up, and then eventually gets to present day. And this is known as the Cassini transition. Okay? Now, when I talked about the spin axis of the moon, a valid question would be, what spin axis? And in reality, when we're talking about a spin axis, what we're really talking about is the spin of the outer solid part of the planet, okay, or the moon. So I'm really talking about the mantle spin axis. So I took that yellow arrow, which went to the center, and I've now plopped it so that it's just on the outer bounding surface here, okay? So that's the spin axis. But if we're interested in the dynamo and the magnetic field generation in the core, then we could also ask, what's happening in the core? That's down here. What axis is it spinning about? Okay? And if you look at this, it turns out that the outer core is not coupled to the mantle in the moon. This is unlike the scenario in the Earth. Okay? In the Earth, the outer core and the mantle are coupled, so they precess together. All right? But in the moon, because the moon's core today is not elliptical enough, okay, because there isn't enough of a rotational bulge on the core mantle boundary, the ellipticity of the core mantle boundary isn't large enough in order to get coupling between the core and the mantle. And there's a condition that was determined by Poincaré and others early on that said that ellipticity, in order to get coupling, has to be larger than the rotational period divided by the precessional period of the body. Okay? And so this condition is not met for the moon. So the outer core is doing its own thing, most likely spinning about the ecliptic normal, okay, while the mantle is spinning about a different axis. So you can envision this as we have two spheres that are spinning about different angles. Okay? All right, so if we were to plot that on this type of diagram again, where yellow was the mantle's obliquity or spin axis angle, then the core would have stayed close to 0. It would have been coupled early on. So I should have mentioned earlier in time the precessional timescales and the rotational timescales and so forth would have been such that they would be coupled, but then they would become decoupled roughly around here. So you can see that there's going to be a time period from about 30 till about, say, 45 or so Earth-Moon separation radii, where the core and the mantle have a large angle of separation between their spin axes. Okay? So there's the core-mantle decoupling. This is the time period that we're interested in for the processionally driven dynamo scenario. Because in order to get energy into the core from the mantle, you want to have a large differential rotation angle between those two. So this is the time period we're going to focus on here just after the Cassini transition. That's what I'm saying there. So what we did was we ran a bunch of numerical dynamo simulations. Okay? But we can't run a dynamo simulation over all this time. In order to work at reasonable parameters for the system, you can't run for very long time periods. So instead what we did was we took a characteristic angle here, say, so this is the obliquity of the mantle. So initially this was about 60 degrees. So we took a simulation and we ran it for some time at 60 degrees angle, and we saw what the equilibrium solution was. And then we ran another simulation, say, at 45 degrees, and we saw what the solution was. And we went forth and did this and used those as characteristics of what the field would have looked like at those times. Okay? The dynamo simulations we use typically, so I've just put up the equations here. Basically, we're solving the momentum equation for the fluid motions and the magnetic induction equation for the magnetic field generation. What else do I want to say about this? And we have the core mantle boundary essentially processing at specific angles and frequencies according to what the lunar history would have given us from the Cassini state scenario. All right, so in order to solve this problem, there are a variety of parameters that we can inflict on ourselves or impose on ourselves. Okay? All these parameters essentially give us ratios of forcings and then also the angle of the precessional motion or the spin axis of the moon. And what I've done here is basically given you what the values are in our models versus what the values should be in the moon. Okay? So for example, we're able to get the right obliquity of the mantle, so the spin axis angles we're able to do properly. Okay? The Poincare number here is essentially a ratio of frequencies. It's the frequency of the precession to the rotational frequency of the moon. And we're also able to get that right. So the value, the difference in, or the range of values here has to do with as the moon moved away, it would have taken on different values from the Cassini state scenario. So we're able to do those properly in our models as well. However, you can't see those lines. There are two numbers here, one known as the Ekman number and the other known as the magnetic Prandtl number. So let's start with the magnetic Prandtl number. The value in our models is 1, whereas I've listed the value in the lunar core is about 10 to the minus 6 or 10 to the minus 5. Okay? This number is essentially a ratio of two different diffusion timescales in the system. Okay? And what this is telling you is that it's very hard in numerical simulations to run simulations with different diffusion timescales going on. However, one could make the argument that if the system is turbulent, then it's not the molecular values of the diffusivities that matter, which is how we got these numbers, but it's the turbulent eddy diffusivity values that matter, in which case your Prandtl number in this case should be 1. So we make what's called a turbulent eddy argument for why we choose a magnetic Prandtl number 1. But if you want the real answer, we do it because we have to, because it's hard to do anything better than that in a numerical simulation. Okay? The Ekman number measures the ratio of the viscous forcings to the Coriolis forcings. And in the moon, this is an incredibly small value. In all planets, this is an incredibly small value. Okay? Our model values cannot be, we cannot make our model values as small as the values in the core of the moon. Okay? We're about 5 to 6 order magnitudes off. All right? However, this is a ratio of different forcings. And essentially what we're saying here is we hope that our viscous forcings are small enough so that they're not affecting the dynamics. So we hope that we're in an asymptotic regime. But even if we're not, what we're going to do is we're going to try a variety of different values for the Ekman number. We're going to see if we can develop a scaling law, and then we're going to extrapolate our results out to real lunar values. Okay? So that's all we really can do. It's a limitation that all dynamo modelers have to live with. Okay? Now, there's also the problem of the inner core radius. Now, this isn't something we initially talked about. I didn't show it on any of those slides for the procession, but as someone who's doing simulations, I have this inner boundary in my model, so I have to care about it. So at the time, we were thinking, well, what are we going to do with the inner core boundary? We don't know the size of the inner core in the moon. Today, we have an estimate from the seismics, the recent study. In the past, we have no idea what it was. So we tried a variety of values. I'm going to show you results from a case where the inner core was about half the size of the total core radius, but we varied this from about 1/4 to about 3/4. The results are different by about a factor of 2. Okay, so it's not a huge issue, but we did include an inner core. Okay, so here now you can see here's the mantle spin axis in our system. Here's the outer core spin axis spinning about the ecliptic normal, and then here's the inner core. And as soon as we added the inner core, we had to ask, well, what's it spinning about, right? We've got the mantle, we've got the core. What's the inner core doing? Okay? The inner core is going to spin based on the net torque acting on the system. Okay? So the types of torques that can act on the inner core, first of all, you've got a viscous torque between the inner core and the outer core. Okay? You have a magnetic torque between the inner core and the outer core. And then you also can have gravitational torques if there are any sort of density heterogeneities in the mantle and there's any sort of asphericity of the inner core, then you're going to have gravitational coupling between them. So these are the possibilities for the torques acting on the system. And in reality, what you would want to do is solve a net torque equation and solve basically torque as I omega to figure out the rotation rate of the inner core. Okay? If you do an order of magnitude calculation of the size of those different torques, you end up finding that the gravitational torque is the largest. Okay? But there are a lot of assumptions that go into that. We decided as a first case scenario to try the scenario where the inner core would be gravitationally locked to the mantle. And so whatever the mantle is doing, the inner core is going to do. Okay? This is a simplifying scenario, but it's probably not a bad one. Okay? There has been some recent work looking at whether or not the inner core should really be locked to the mantle. It turns out to be a little more complicated than just the magnitudes of the different forcings. You have to care about things like the inner core nutation frequency relative to the processional frequencies in the system. And this paper by Dunbury and Wazorek have looked at this recently, and they've shown that today they're no longer perfectly locked. So the inner core and mantle are no longer locked today, but in the past they could have been. But there needs to be a lot of work still done to try and understand that. But we're going to assume that they're locked. Okay, so here's a setup. I'm going to try and show you some results, but just to give you an idea. So the rotation axis of the moon is going to go up and down here. This is the core mantle boundary of the moon. This is the inner core boundary of the moon. Okay? When you're doing a numerical simulation, you have to worry about things like boundary conditions on all of your variables. We're going to use something called a no-slip boundary condition on the core mantle boundary. Basically, whatever the mantle is doing at this boundary, the fluid underneath it has to be doing. Okay? And we need this in order to couple the mantle motion, which is out here, the precession of the mantle, to the core. Okay? So that's how we're getting that mechanical driving into the system. In our first scenario, we're going to take the inner core and we're going to try and make it as passive as possible. We know we want it in the system, but we don't want it to have too much of an effect, so that we can figure out what is just the effect from this outer boundary. So initially, we made this inner core electrically insulating, so it has no magnetic effects. And we also used what's called a free slip boundary at the inner core boundary, which essentially means that there's no shear stresses on that boundary. Okay? So we ran that, and what we found, this is from sort of our toughest values of these parameters, the Ekman magnetic Prandtl number, and our largest spin angle for the moon. And these are streamlines of the velocity fields. And what you're supposed to see from this is that these are very simple. This is just like a nice overturning here, a nice overturning here. And when you have a velocity field like this, your magnetic field is not self-sustaining. It decays away. Okay? And it turns out with these parameter values, we're not in the right sort of parameter regime in order to get the precessional instabilities we were trying to get for the moon. There are certain parameters that we know you have to meet in order to get this precessional forcings. The most important thing is that you need to have a really small viscous force. And the main problem here is that our Ekman number, which represents the ratio of those viscous forces to Coriolis forces, is too big. So in our models, we can't generate precessional forcings due to this outer boundary connecting to the fluid motion and churning motions in there. That doesn't mean it's not possible for the moon. That's still an open question. But in our models, we weren't able to do that. So we couldn't excite the instabilities that we wanted to in order to get the motions. However, we decided to look at a case where the only change we made was we made the inner core electrically conducting. So this means now that the inner core and the outer core can couple magnetically. And as soon as we did that, without changing anything else, we suddenly got all sorts of small-scale fluid motions in here. Okay? Now remember, the inner core is going to be doing whatever the mantle is doing. So there is a way of kind of connecting the mantle to the outer core with this mechanism by first going through the inner core. That's the difference in this scenario. Okay? And not only did we get a lot of small-scale motions, these are maps of the magnetic field inside the core. We also got magnetic field generation. So we were able to get a dynamo from this mechanism. Okay? Then, as a test, what we did was we said, well, what if we take that outer boundary and we make it free slip, essentially decoupling the mantle, which is out here, from the core at that outer boundary. So now the only way that the mantle's precession is being felt by the outer core is through its influence on the inner core, okay, through that gravitational locking. And we did this, and what we found was we got even more magnetic field generation. In fact, it filled the entire cavity rather than just having it centered near the inner core boundary. Okay? What we think was happening there was, again, because our viscous forces are too strong in the model, having that coupling at this outer boundary essentially just damped out a lot of the motions near that boundary because of the viscous dissipation there. So when we got rid of that, suddenly this inner core was able to churn the motions and it could fill out the entire cavity. So we've essentially in some ways found a new instability. Okay? It's due to having core mantle boundary and inner core gravitational coupling plus inner core, outer core magnetic coupling. Okay? So you need two ingredients in order to make this recipe. This is a terrible name for an instability, and we're trying to think of a better way to describe it, but that's really what it is. Okay? So with that now, what we did was we ran a series of simulations with different values for our parameters, and we looked at when do you get a dynamo. Okay? So this is that spin angle obliquity here. Okay? This is rotation rate of the moon, which you can get by, which is non-parameterized in the model using that Ekman number. Okay? All of the white circles on here are dynamos that failed, cases where we didn't get magnetic field generation. All of the black circles are dynamos that lived, where we were able to get magnetic field generation. And you can see that there seems to be, we've drawn in this boundary here, which is like a threshold between scenarios where you would get dynamo action and scenarios where you wouldn't get dynamo action. Okay? Now what we can do is look at where is the moon in this phase space. And the moon, near the Cassini transition plots here, and then over time, as the obliquity angle decreases and the rotation rate changes, the moon follows this path. Okay? So what this suggests from here is that there would have been a lunar dynamo from our mechanism early on, up until about a time when it was at 42.5 Earth radii separation. Okay? And then it essentially gets into the regime where there is no dynamo at present day. Okay? In our mechanism, you need something near the center that has differential rotation. So if you can find a way for me to get sharp differential rotation at the deep interior without a solid inner core, then it's not essential. But I can't think of another way to do it. All right, so this is sort of just a parameter space showing us where we get dynamos. We can also, from our simulations, figure out what the surface field intensity would have been in our models. Okay? So we did that here. So again, this is that rotation rate parameter. And then here is the surface field intensity from our simulations. And what you're seeing here, the different colors represent different angles of that obliquity. So that was the other axis in this case. So 60 degrees was the highest angle we saw, so that would have been right after the Cassini transition. Then 45 degrees is a little bit further away, and then 30, and then 15. Okay? The two lines here are those scenarios with that different coupling at that outer boundary. Okay? So I can give you an idea of the range here. So all of these dots filled in here are from our simulations. And you can see in this log-log space that they seem to plot on straight lines. And that gave us confidence that we could do this extrapolation. So these dashed lines are extrapolations. And these are the values of the rotation rate that the moon would have had at different separations. So the outer one here is near the Cassini transition, and this is at about 42.5 Earth radii, where the dynamo mechanism then died away. So what you can see is that you start with very intense fields, and then as time goes on, as you move further away, the fields get weaker and weaker and weaker. Okay? But the intense fields initially are quite strong, tens of microteslas. Okay? So if you're thinking, going back to the lunar paleomagnetic record, Okay, so again, we had time before present, and we had surface field intensity, and these are the samples. Okay, in order to compare our model results to this scenario, our issue is that we have results where our x-axis is Earth-Moon separation. It's not time, right? So you need to convert from Earth-Moon separation to time, and that's not easy. In order to do that, you need to know a lot about tidal dissipation in the Earth for the system to evolve. But people have done this, okay? So for example, I'm going to take this data, and I'm going to replace this axis with the time axis, and I'm going to move this, with the Earth-Moon separation axis, and I'm going to move the time axis to the top, okay? So this is exactly the same points, exactly the same time bits before, but now I've converted to semi-major axis distance based on time axis used in this model by Dwyer et al. Okay? But there is other work that suggests you could have a difference here. Okay? If you make different assumptions about the Earth, you could actually get a different shifting. So what I'm going to do here is I'm going to plot the exact same points, but on a different conversion axis. And that's what these orange points are. Okay? So if you believe the model by Walker, 1983, then you believe that these points fall at these locations rather than at the black locations. Okay? So they're the exact same data, just plotted on two different scales. And we did this so that we could compare to our model. All right? So here's where our model, here's where the previous work had suggested. So for example, here was the thermally driven scenario, right? Here was the inner core crystallization or the compositionally driven dynamo scenario. Here was that Dwyer et al. Processionally driven, mechanically driven scenario there. Okay? So those were the intensities that were expected from scaling laws. And here's where our results fall. Okay? So again, the red and the circles and the squares are those two scenarios for that outer core matching. So you can imagine it's somewhere in between there. But we start with very high field intensities that can explain the data, especially if you like the orange time axis conversion. And then over time, eventually, the fields get weaker and weaker and eventually stop. Okay? So our mechanism is able to both reproduce the intensity of the field early on, but also the rapid decline of the field to a much weaker state or no state afterwards. With this mechanism, we cannot explain any magnetism at later times. In order to do that, you would have to invoke either thermal or compositional driving for the core. Okay? And it's probably a combination of both. But this mechanism can explain the early time period. Now, you might wonder why this mechanism is so much better or able to get such stronger fields compared to the other mechanisms. And I think the answer to this is that with processional forcings, with mechanical driving in general, you're able to tap into the rotational energy in the system, right? With other scenarios, it's really hard to tap into the rotational energy. And if you have the rotational energy, then you have a big energy source that can create a strong field. All right, so the conclusions of my talk, we found that a mechanical dynamo powered by mantle precession, as long as you have a gravitationally locked inner core, is capable of explaining the high intensity of the field early on, as well as its precipitous decline after about 3.5 billion years ago. The Lorentz torque at that inner core boundary, because you've got that inner core rotating relative to the outer core, that creates a lot of stretching of magnetic field lines there. That really has a big effect on the generation of fluid instabilities and magnetic field instabilities in our scenario. What this means is that, for other planets, if you believe this mechanism might work, it's really important to consider the inner core if you're doing any sort of processional type dynamo simulations or other types of mechanical driving sources. In terms of future work here, there are a few things we'd like to do. We'd also really still like to get a sort of a pure processional dynamo scenario. There have been a few studies out there of people who have gotten them, and people are doing initial studies with that, but it's hard. Okay? It turns out to be much easier if you can work in a non-spherical geometry. So it'd be great if we could start maybe including topography on our core mantle boundary or ellipticity. Okay? We're much more likely to get processional instabilities from this. Okay? That would just add to our system, right? We're not trying to replace it. We're just trying to add other ingredients. Also, rather than just automatically coupling the inner core to the mantle gravitationally, we'd like to dynamically calculate that torque in real time, and that can be done in the simulations. We just have to make assumptions of what the density heterogeneities are in the mantle and what the non-sphericity of the inner core is. So the reason we haven't done that yet is because we don't really know what to assume. But physics-wise, it would be better if we did that. Okay? We'd also like to combine this mechanism with regular convection due to either thermal or compositional buoyancy to see whether or not how they play together, right? It's possible that these two mechanisms can co-add and you can get even stronger fields. It's possible that they work against each other, okay? So, and we don't really know until we try and couple them. And then finally, with this type of instability, it'd be nice to just do basic scaling studies of it so that That's right.
What does that mean?
So the good thing is the Cassini transition happens relatively late, right? So you have time for it to start growing, in theory, but you'd have to do a real thermal evolution model to figure out when it starts nucleating and grows from there, right? And you're right that depending on the growth rate, it could be different sizes for different precessional angles in the history. We haven't tested that. We've just taken each of those and done different inner core sizes for each of them. You get, again, a factor of 2 difference, but you're right that would be another factor to include. Yep. Yeah, so there's 2 things that partial melt layer could do. First of all, it could allow the core to cool a little bit quicker because it'll just have faster heat transport properties. And if it has some conductivity, the question is how conductive is it, right? So even in Earth, the lower mantle has some conductivity to it. And so people, in our numerical simulations, for example, we can include an electrically conducting solid layer surrounding the core. But you usually make the conductivity of that region quite weak compared to the core, so say a factor of part in 10 to the 5 or so. And what you can find then is you can cause angular momentum transport between the mantle and the core that way, okay? But it doesn't really affect the dynamics going on in the core too much. We haven't tested it for the moon. That might be I said I needed a lot of shear and an electrically conducting region. I guess that could be the core mantle boundary region, but you need that layer to be very metal rich or very electrically conducting, and I don't know that it would have that property. Yeah, I mean, these are great questions. So we haven't included any sort of tidal dissipation or anything in our models, right? But the question is, how fast does the inner core, say, relax its shape if it's super rotating relative to stuff? But I think ultimately its equilibrium shape is going to be determined by the gravity of the mantle, right? Because it's going to be an equilibrium. The shape of the inner core is going to be an equipotential surface. So you need to figure out what the gravitational potential is at any point in time, and then how long it takes for the inner core to adjust its shape as the mantle is moving around. So these are great questions that I have no answers for in terms of what to do. So what I would say is that these 2 different points, I think, assume something different about Q of the Earth or something in there, right? I would say our data isn't good enough I wouldn't sit here and say whatever was assumed in the orange paper must be right and not in the other paper. So yes, I think it could put constraints, but I don't think we have good enough constraints from this type of mechanism to do that. I don't think you'd learn anything from just doing this. But in principle, yes, that would work.
Looking at the data, it looks to me like it's sort of like a light switch. It's got high values early on, and then the heat turns off. The kind of mechanism you're describing, is there a way to have it shut off?
Well, it'll shut off as soon as, oops, not good with buttons. In our mechanism, it'll shut off as soon as this angle gets too small. So when it gets to about 10 degrees, it shuts off. But these data that, it seems like it goes from here, and then no one knows if these are here or if they're down here, right? There's been some new work that I haven't put on here by Weiss's group and colleagues that I think have some points in between here that seem to suggest, there's some falling here. But you're right that I've got a trend going down here where it seems to be flattened and then down. But there are error bars on all of this, which are fairly large. So, but you're right. I'm not in my mechanism. I can't do flat. I can't do a step jump type of thing. I have to do sort of a steady decline. We have no. So, what's your mechanism to drive the dynamo then? No, because we have no buoyancy in the system then. No. So we're assuming a neutrally stable background. So we have no possibility of convection or anything else generating other fluid motions. Yeah, that's a great question. So that's our next step, is to look at the morphology. These are, you can probably look at these and get in. So these are the poloidal components of the field. So you can see it's smaller scale than a dipole, so this is going to be a non-dipolar field. This is a snapshot, but it is a non-dipolar field. But this summer I've got an undergraduate student who's going to go through this, look at the morphology in more detail, and try and figure out what the implications are for true polar wander studies of the moon. That's the one with the no slip outer bound. And then that's the one.